Welcome students, welcome to today's session of ALPHORES e-learning program. In this session, let us continue with the applications of thermal expansions of solids. Now, in today's class, let us discuss about what is known as differential expansion and its application. Differential expansion and the applications of this. So what is meant by differential expansion? Let us consider two rods of same initial length. Let us say L1, let us say initial length is L, and another rod also having the same initial length L. But the first one is made up of a material of coefficient of linear expansion alpha 1, and second one is made up of another material of another coefficient of linear expansion, let us say alpha 2. So alpha 1, alpha 2 are their coefficient of linear expansions. Now let us increase the temperature for both the rods by delta T. So here temperature change is the same for both of them. Even though the length is initial length is same and change in temperature is also the same, if you consider the expansions, let us say delta L1 is the expansion the first one, let it be L alpha 1 delta T. L alpha 1 delta T is the expansion of the first one. Corresponding to the same change of temperature, expansion of the second one delta L2, it is L alpha 2 delta T. Very clearly, even though their initial lengths are same, as coefficient of linear expansion is different, their expansions are also different. Let us suppose you take a condition where alpha 2 is greater than alpha 1. That means the second rod is having larger coefficient of expansion than the first one. So clearly, because of larger value of alpha, it expands more. It expands more than the first one. So finally, there will be initial length are the same, but finally the final lengths are not same because their expansions are different. Therefore, if the final length of the first rod, let us say L2, that is L plus delta L2, and for the first rod the final length L1, that is L plus delta L1. Now if you consider the difference in their lengths, initial lengths are same but final lengths are different. So if you consider the difference between their final lengths, that is clearly L2 minus L1, that is L plus delta L2 minus of L plus delta L1, which is the difference between their expansions delta L2 minus delta L1. So this is known as differential expansion. That means when compared with one rod, what is the expansion of the other rod? When compared with the first one, what is the expansion of the other? So then in such a case, very clearly substituting these values, this is L2 alpha 2 delta T and this is L1 alpha 1 delta T. Otherwise, initial lengths are same here. So L alpha 2 delta T here and this is L alpha 1 delta T. Otherwise, the differential expansion is L of alpha 2 minus alpha 1 into delta T. This represents the final difference in their lengths. Initially, they are having the same initial length. The change in temperature is also the same. But because of different coefficients of expansion, there is a final lengths are not same and there is a difference in their final lengths. And this difference in the final lengths, this is known as differential expansion. Differential expansion. Now, let us discuss about applications of this differential expansion. Now, let us consider an important application, that is, consider two different materials. If you consider iron and brass. Generally, brass will have larger coefficient of expansion than iron. even if you take the same initial length for both the rods, because of their expansions, different expansions, both of them will be expanding differently. And in such a case, as brass expands more and iron expands less, let us consider a small application where we can have numerical examples. For example, there is a brass rod. This is a brass rod. It is having a length 1 meter. I am measuring the length of this broad rod using an iron scale. This is iron scale. And let us suppose at some room temperature 20 degrees centigrade, both are having the same length, and this iron scale gives the correct length at the temperature 20 degrees centigrade. That means the iron scale is graduated at this temperature 20 degrees centigrade. Then as at this 20 degrees centigrade, this iron scale, this one end is 0, this end is 100, and the length of the iron scale is 1 meter. And similarly, because both are having same length, the length of the brass scale is also 1 meter at 20 degrees centigrade. Initially they are having the same length. Now let us suppose we have increased the temperature of both the steel rod or iron scale and the brass rod. This brass rod and iron scale, let us increase the temperature to some high temperature around 120 degrees centigrade. Clearly there is a change in the temperature by 100 degrees centigrade. Because of this 100 degrees centigrade change of temperature, both of them will expand. Brass expands more than the iron. Because of larger value of alpha, brass expands more. Then let us see what will be the final situation. If you consider the brass, suppose it expands like this. This is the final length of the brass. Final length of the brass. But iron scale will also expand. But because the iron scale has a smaller expansion. Now, as we have discussed about the scales previously, let us understand one important point there that we have discussed when we are studying about the metal scales. All metal scales are graduated at a particular temperature. At that temperature only they give the correct reading. But we know that our scale is graduated at 20 degrees centigrade. So at 20 degrees centigrade only it gives the correct length, and that is 1 meter, because we are using the scale at 20 degrees centigrade only. But now we are using it at a temperature 120 degrees centigrade. So corresponding to the change in temperature, the length of the iron scale that will also increase. But practically the length, the distance between successive graduations, that will increase. This end will always show 0, this end always show 100. Therefore, now this scale represents a reading 100 only. But now what I want is, I want the length of this brass rod as measured by this iron scale. I want the length of the brass rod, but as measured by the iron scale. Because initially both are having the same initial value, same initial length. This is 1 meter. But now even the iron scale expands, this end remains 0, this end remains 100 centimeter. So it appears as if length of the iron scale is remaining as 1 meter. But beyond that the brass scale is expanding. Therefore this part is addition. This part is addition, let us say x. So when compared with the this iron scale, the length of the brass scale is more, by a value equal to x. So as measured by this brass scale, this iron scale, as measured by this iron scale, if I want the length of this brass rod, because it is expanding more by a value equal to x than this iron scale, the length of the brass rod as measured by the brass scale becomes 100 plus x. 100 plus x. Because both are initially having the same length, but now both are expanding. But I want length of this brass scale as measured by this brass rod as measured by the iron scale only. So this iron scale, at this end it is 0 now, and this ended it is 100 now here. So this is the additional part, and that additional part is nothing but differential expansion of this brass rod and the iron scale. The differential expansion that must be added. So this is 100 plus 100 of alpha of brass minus alpha of iron multiplied by change in temperature delta T. So just by adding this differential expansion, you can consider that the length of the brass scale you can measure as per this iron scale. So length of the brass rod as measured by this iron scale at the higher temperature is the reading given by up to this point is 100 plus this additional value. The additional value is nothing but differential expansion of the brass rod and the iron scale. So like this we can apply the concept of differential expansion to measure the length of one rod made up of another scale. Both are made up of different materials. So it is 100 plus the differential expansion. Now there is a possibility that there can be a different case where the brass scale, suppose you are using and you are measuring the length of iron rod, and the scale is made up of brass and this is a rod made up of iron. Then what we have to do? Now what happens is the brass scale, suppose it is also graduate at 20 degrees centigrade, it gives the correct length, so that this end reads 0, this end reads 100 centimeter, so that length of the brass scale is exactly 1 meter at the temperature at which it is graduated, and you are measuring at 20 degrees centigrade itself, so it gives the correct length. And the correct length given by the brass scale when you are measuring the length of this iron rod is exactly 1 meter. Remember, we are using a brass scale and we are measuring the length of iron rod. This is the story at 20 degrees centigrade. Both are having the same length. But when you are measuring at 120, let us see what will happen. I am using the same change in temperature. Temperature is increased by 100 degrees centigrade. Now what happens? Brass expands more. Brass expands more than the iron. Then what will be the result? Suppose brass expands this much as we have shown previously. So this is the length of the brass rod 0 to 100. As I told you, length of the scale appears to be remaining as a constant at all temperatures, because one end will always be 0, other end will always be 100. But now the iron rod thus expands only by this much. This is the iron rod and this is the brass scale you are using. Then what happens? Very clearly, brass rod is having a length up to this point is 100. But as measured by this brass scale, when you take the length of this iron rod, it is only up to this point. Therefore, it is nothing but the length of the iron rod is smaller. Length of the iron rod is smaller than the length of the brass scale by the same amount x, which is the differential expansion. Very clearly, if you want the length of this iron rod as measured by the same brass scale, let us say L dash equal to initial length is 100, but very clearly up to this point it is 100. So this part is deficient. This part you have to subtract. So it is 100 minus x. 100 minus x. Very clearly 100 minus, what is this x? We know it is the differential expansion of the brass scale and the iron rod corresponding to this change of temperature 100 degrees centigrade. So very clearly it is the initial length of alpha of brass minus alpha of iron or steel multiplied by change in temperature 100. By substituting all these values, we can calculate what is the final length of this iron rod as measured by the brass scale. Practically, initially it is 1 meter. Because of change in temperature, it must be more than 1 meter. But what we are asking is length of this iron rod as measured by the same scale, because the scale is expanding more. So the length of this iron rod will be something less than the 100 centimeter. So 100 minus x. This x is nothing but differential expansion between the two materials corresponding to the same initial length. Then you will get the final length of this iron rod as measured by the brass scale. So this is very clearly a better application of what is known as differential expansion. Now after this let us move on to another important application related with the differential expansion that has a practical application in the day-to-day appliances that we are using. In all refrigerators or electrical iron, you know, after a particular temperature, required temperature is reached, automatically the circuit is switch off. You need not every time, you have to switch on and switch off every time. Just if you keep the plug placed inside the pin, automatically you will be getting the current, and as the required temperature is coming, automatically switched off, there will be no current. And again after some time, if the temperature is decreased, again to increase the temperature up to the required level, automatically it is switched on. All this it is happening only because of a particular device that is called bimetallic strip. Bimetallic strip. This is also an important application of this differential expansion. Bimetallic strip. What is this? As we have discussed now, brass expands more than the iron or steel. Generally, their expansions coefficients will be in the ratio 3:2. Brass and steel, or brass or iron, generally they will be in the ratio 3:2. Brass expands more. Now, what we will do here? We take small strips, a thin and small strips of the steel or iron and brass, and they are riveted together at high temperature, so that suppose this is a small, the thickness should be small. It is a brass strip. To this an iron strip is connected. This is made up of steel or iron. Generally both of them will be having the nearly same value of alpha. We can use any brass of iron or brass or steel also. Now the two strips when they are in the red hot condition, that is when heated to high temperature, they are placed one on the other and hammered until they are combined with each other, so that you will have a strip like this. One is placed on the other. It will be consisting of two layers, and the thickness, total thickness, let us say it is T. It is T. Now both are combined as a single body. Now what is the importance of this bimetallic strip? Now suppose the temperature is increased. When the temperature is increased by large amount, we know brass expands more and steel expands less. As a result, what happens? Both of them will have different length. Final lengths are not the same. Initial length are same now here at the room temperature, but their final lengths are not same. Then what happens? As brass expands more, it should have more length than the steel. But they should be combined, they should be united as a single body. They should behave like a single body only. They should be connected to each other. They should have act like a single body, but both of them should have different lengths. That means they are combined like this as two strips placed one on the other like this. Then how this is possible? Then to make it convenient so that both of them will have different lengths and still they are kept united. Slightly it will be bending like this. It will be bending. Now what happens is, to understand clearly, let us have like this. When it is bending, it will be bending like this so that you will have the larger length present outside and smaller length present inside. So that here, as brass expands more, you will have brass present on outside and the steel present on inside. Very clearly, you know, when they are meeting at some point here, the arc length here, because the radius is less, arc length is less in this spot and arc length is more in this spot. So that the brass will have larger length and the steel will have smaller length. It will be bending like this. So when you are increasing the temperature, when it is heated, when it is heated, it will be bending like this. Brass will be present on outside and the steel having lower value of alpha, it will be inside. And now suppose it is cooled. In refrigerator also we will have a same condition. In refrigerator also, after some time when the chamber is cooled to the sufficient limit, automatically the power is switched off. And after some time, suppose you are taking the door open and closed for some time, the temperature may increase and again automatically it is switch on. Automatically switch off and switch on, and this is called thermostatic action. Thermostatic action. That means you are trying to keep the temperature as a constant. For that purpose, thermostatic action, we can use this bimetallic strip. And now when the temperature is decreased or it is cooled by a high temperature change, then what happens? When they are cooling, what happens is, remember that alpha, coefficient of linear expansion, is a measure of change in the length. So when you are increasing the temperature, it expands more when alpha is more. Similarly, when alpha is more, when the temperature is decreased, it contracts more. Therefore, remember, a substance or a metal which expands more also contracts more because alpha is large. So here brass is having a larger value of alpha. Brass is expanding more because of increase in temperature. Similarly, when temperature is decreased, brass should contract more. As a result, brass must have smaller length and iron is not contracting that much. So though initial lengths are same, as brass is contracting more and steel is contracting less, the final length of the steel strip is more than the brass strip. Then what happens? To have a larger length, the bimetallic strip will be bending such that you will have the larger portion present outside and a smaller portion present inside, so that the larger one is the steel and the smaller one is brass. They are placed like this. So it is bending such that the steel is outside. Remember that always the larger part must be outside and smaller part it should be inside. So here if you consider like an arc of a circle, because of larger radius here length is more, and because of small radius length is less here. So as brass is contracting, brass is having smaller length than the steel strip, so that steel is present outside and brass is present inside. So here very clearly they are bending in two different ways. When it is heated, it is bending such that brass is present outside, and when it is cooled to a low temperature, it is bending such that steel is present on the outside. Like this, this bending can be used to keep the system or keep this bimetallic strip used as a thermostat. For example, in a electrical iron, when we want a particular temperature for silk cloth or some thick cotton, we need different temperatures. So when you are using electrical iron to make these to iron these different types of cloths, then what we have to do? What we have to do? We will be using a thermostatic operation where automatically the current power is switched off by using the phenomena of thermostatic action of this bimetallic strip. What we will do is in the electrical circuit present, there will be a thermostat like this. It is a bimetallic strip, and this bimetallic strip is placed in contact with a fine tip which is connected in the electrical circuit. Now when because of high temperature, the temperature is increased, they will be expanding differently. This is brass and this is steel. Due to change of temperature, this brass will be slightly bending at the end. It bends slightly like this. When it bends at the end point, the bimetallic strip appears to be like this. As it is bending at the end point, the contact is lost here. When the contact is lost, the circuit becomes open. There will be no power passing in the circuit. And once again, when the temperature comes down again, getting cooled, the bimetallic strip will go back to the normal position, and it will, when it goes back to the normal temperature, it will restore the normal length, so that again this contract is developed and circuit, the current will be passing. And now finally, before we close, let us, when it is bending, we have taken the bimetallic strip like this. Let us say that T is the thickness. When it is bending, what will be the radius of curvature of this bending? When we measure this radius, let us say alpha of brass is alpha B and alpha of steel is alpha S. Corresponding to a change in temperature delta T, the radius of curvature of this bent bimetallic strip that we can calculate from the equation, the thickness of the entire system, that is the thickness of the bimetallic strip is T divided by alpha of brass minus alpha of steel multiplied by delta T, where delta T is the change in temperature, T is the thickness of the bimetallic strip. That means sum of the thicknesses of both the strips, and alpha B is the coefficient of linear expansion of brass, and this is the coefficient of linear expansion of steel. By substituting, we can find out the radius of curvature of this bimetallic strip. So with this, let us stop today, and in the next class we will continue with the other applications of the thermal expansions of solids. So let us stop here, and next class we will continue with some more applications of thermal expansions and also some numericals. Right? Thank you.